If you could fly straight out from the Sun in the direction of Pluto, the solar system would not end where most diagrams seem to stop. Neptune would fall behind you at about 4.5 billion kilometers. Pluto would become a distant point of ice and shadow. And near 7.5 billion kilometers from the Sun, you would reach the region many textbooks once treated like the outer edge of the Kuiper belt, a strange drop-off known as the Kuiper Cliff. For years, that edge looked real. Beyond it, the maps grew quiet. Fewer worlds, fainter objects, a long dark gap before the distant Oort Cloud. But that picture is now coming apart. Tonight, you will meet the edge of the solar system that suddenly stopped behaving like an edge. The Dutch astronomer whose 1951 paper gave this frozen region its name, and the New Horizons linked survey that quietly stacked thousands of images together to pull unexpected worlds out of the dark. The Kuiper belt is bigger than the diagrams ever told you, possibly much bigger, maybe even shaped like two belts with a strange empty gap between them. Let's walk into it. If you enjoy slow journeys through the quiet edges of the cosmos, tap like and subscribe so the channel can keep finding the people who like these long walks. Now, settle in. Let the room get warm. Let the lights go low. We begin. You have seen the picture 100 times. A diagram of the solar system, the Sun at the center, the 8 planets arranged in their familiar rings. And then, just past Neptune, a faint smudge labeled with 2 words, the Kuiper belt. Sometimes the diagram bothers to draw it as a small circle of dots. Sometimes the diagram only writes the name and trusts you to imagine the rest. Either way, the picture does its job. Your brain accepts the smudge as a tidy thing. A ring of leftover ice somewhere out there past the last planet. A place that exists but politely. A place you will never go and never need to think about again. That picture has been wrong for a long time. Not wrong in the way a cartoon is wrong. The Kuiper belt is a real region. Pluto is really there. So are tens of thousands of other small icy worlds drifting through orbits that take centuries to complete. The diagram has the location more or less correct. The problem is what the diagram leaves out. The shape, the thickness, the number of worlds. The fact that the edge of the belt, the place where the dots stop on the page, is a feature nobody has been able to fully explain. The fact that beyond that edge, in a region the textbook marks as empty, telescopes have started finding things. Tonight, we are going to walk slowly through that picture and find that almost none of it is what it looks like. We will not start at the edge. We will start at the most famous resident of the belt. The world that, for a very long time, was the only thing anyone knew, lived out there. His name was Clyde Tombaugh, and in February of 1930, he was a young man working at the Lowell Observatory in northern Arizona. His job was tedious. He had to take pairs of photographic plates of the same patch of sky, taken nights apart, and compare them, looking for any faint dot that had moved between the 2 images. Most of the dots were background stars. Stars do not move from night to night. The one that did was the one he was looking for. One afternoon, in a basement room of the observatory, Tombaugh found his moving dot. A small point of light, far past Neptune, drifting slowly against the fixed stars behind it. It was the 9th planet. It was named Pluto for the Roman god of the underworld, and for most of the 20th century, that was the answer to the question of what existed past Neptune. Just one world, small, distant, cold. For more than 80 years, that was all anyone knew about Pluto with any directness. It was a single faint dot in a telescope. Its diameter could only be estimated. Its surface was a mystery. Whether it had moons was a question that took until 1978 to begin to answer. By the early 2000s, Pluto had a family of small satellites, but it was still, in every meaningful sense, a point of light, not a place. Then, in July of 2015, a small spacecraft called New Horizons arrived. The images came back over weeks as the spacecraft slowly downloaded its data across the long darkness between Pluto and Earth. The world that had been a dim dot for 85 years suddenly became a place. Pluto had mountains, not small bumps. Mountains made of frozen water rising sharply against an icy plain, casting shadows in the weak sunlight of the outer solar system. They had ranges, they had ridges, They looked, in some images, almost familiar, like a photograph of the Earth taken at very low temperature. Pluto had a heart, a vast, smooth plain of frozen nitrogen, shaped a little like a heart, bright against the darker terrain around it. It was bigger than the country of France. Inside it, the nitrogen ice flowed slowly, in great circulating cells, like the convection patterns inside a pot of boiling water turned down to the lowest possible setting. The plain was active. It was rearranging itself, very slowly, in the dim cold. Pluto had a sky, a thin nitrogen atmosphere, blue at the edges in the spacecraft's images, with layered hazes drifting at high altitudes. The atmosphere froze and unfroze with the seasons. In some places, snow fell, not water snow, methane and nitrogen, falling gently and slow, freezing flakes through air thinner than anything that exists on Earth. The bright, heart-shaped plane was given a name, Sputnik Planitia, after the first satellite that humans ever put into orbit. It sits in a roughly 4-kilometer deep basin, possibly excavated long ago by the impact of a large body. The nitrogen ice inside it is many kilometers thick. Slow heat from below stirs the ice, breaking the plane into faint polygonal cells the size of small countries, slowly turning over on timescales of about 500,000 years. From orbit, the cells look almost like the surface of a frozen pond after a long winter. None of this was supposed to be there. Pluto was small, smaller than Earth's moon. The textbooks had imagined it as a dead, frozen rock, geologically inert, far too small to have anything like weather or active surface processes. That picture had been the consensus for decades. Then a spacecraft flew past it and showed that the picture was wrong in almost every detail. This was the first hint that the outer solar system was not the place we had thought it was. If a world this small could be this complicated, what was happening on all the other small worlds out there? And how many of them were there? The spacecraft that had answered the first question kept flying. It had another 4 years before it would meet its next companion. The spacecraft is small, about the size of a grand piano, powered by a single canister of plutonium that generates roughly the heat of a household light bulb, built by an engineering team at the Johns Hopkins Applied Physics Laboratory and launched from Cape Canaveral in January of 2006. When New Horizons left Earth, it was the fastest object ever launched into space. It crossed the orbit of the Moon in 9 hours, a journey that had taken the Apollo astronauts 3 days. It crossed the orbit of Jupiter in just over a year. It spent the next 9 years sailing outward through the empty volumes between Jupiter and Pluto, carrying a small payload of cameras and spectrometers sleeping for most of the trip, occasionally waking to check its instruments and confirm it was still on course. It reached Pluto in July 2015. It did not stop. It could not. The fuel required to brake at Pluto's distance would have been impossibly heavy at launch, so the mission was designed as a flyby. A few hours of close observation, capturing as much as possible, then onward. For most spacecraft, that would have been the end. New Horizons had completed its primary mission. Pluto had been mapped. The data was on its way home. Mission accomplished. But the mission planners had been thinking ahead. The Kuiper belt was full of small objects. If they could find one along the spacecraft's outbound trajectory, the craft might be able to fly past a second world before its instruments wore out or its power supply weakened too much. The team began searching, years before the Pluto flyby, for any small icy body that lay within reach of the spacecraft's remaining fuel. They found one. A tiny object only about 30 kilometers long, sitting at roughly 44 astronomical units from the Sun. It had no name yet. It had only a designation 2014 Mu-69, given when the Hubble Space Telescope had first spotted it. Later it would be named Arakoth, a word from the Powhatan and Algonquian languages of eastern North America that means sky. On the first day of January 2019, New Horizons flew within a few thousand kilometers of Arakoth. The images came back slowly, again. The spacecraft was now so far from Earth that radio signals took 6 hours to travel each way. Sending the full dataset back took months. What the images showed was strange enough that the science team needed time to understand it. But by then, New Horizons had already continued onward. The spacecraft kept flying deeper into the Kuiper belt with no further targets confirmed. Its instruments kept measuring. Its radio kept reporting. It is still out there now, more than 60 astronomical units from the Sun, traveling outward at roughly 50,000 kilometers per hour. From the spacecraft's perspective, the Kuiper belt is not a crowded place. The icy worlds out there are spread across an enormous volume of space, and the distances between them are vast. New Horizons can fly for years without coming anywhere near another object. Most of the time, the nearest body is millions of kilometers away. The belt, seen from inside it, is mostly dark. But the dark is doing something. Every measurement the spacecraft takes refines what we know about the outer solar system. The dust counts. The cosmic ray fluxes. The local magnetic fields. The faint background light, which turns out to be brighter than expected, suggesting that more material is drifting out there than anyone had thought. The spacecraft will keep doing this for as long as its plutonium holds out. Into the 2030s probably, maybe longer, and the small companion it visited 4 years after Pluto turned out to be one of the most important objects ever directly imaged in the outer solar system. Arrokoth is shaped like 2 pancakes pressed together. That sentence does not do justice to it, but no better one exists. In the images New Horizons sent back, the object looks like 2 flattened spheres joined at a thin neck, sitting in the dark at an angle, glinting faintly in the reflected light of a very distant sun. It is small, only 35 kilometers long, the kind of object that, in any other context, would barely be worth a footnote. But Arrokoth is not any other object. What it is, what it has always been, is undisturbed. When the solar system formed, 4.5 billion years ago, small icy bodies condensed out of the gas and dust around the young sun. Most of them eventually collided with each other, breaking apart, sticking together, building up into larger bodies, and finally being either absorbed into the planets or thrown out into the wider belt. The smaller objects either got destroyed or were heated and altered by collisions. Arrokoth was not. Its shape suggests that it formed gently. 2 smaller icy lumps, drifting through the early outer solar system at very low speed, came together and stuck. They did not crash. They did not deform each other significantly. They simply met and stayed. This is important because, for decades, planetary scientists had argued about how the icy bodies of the outer solar system actually formed. One school of thought said that small lumps slowly grew larger by hitting each other again and again, sticking together in violent collisions over millions of years. Another school said that large clouds of pebbles collapsed quickly under their own gravity, producing bodies that were essentially born almost full-sized. Arrokoth's shape is evidence for the second model. Its 2 lobes are too pristine, too gently joined, to have formed in a long sequence of violent collisions. They formed quietly, from a slow inward drift, and have been undisturbed ever since. Then nothing happened to it for 4.5 billion years. Sit with that for a moment. The Earth, in the same span of time, had its atmosphere change 3 or 4 times. It had oceans appear, freeze over completely, melt again. It had continents form, drift apart, collide, drift apart again. It had ice ages. It had warm periods. It had at least 5 mass extinctions. It had the entire evolution of life, from single cells to fish, to forests, to mammals, to whatever is sitting in your chair right now, reading or listening to this. Arrokoth, in that same time, did nothing. It drifted around the sun on a slow, almost circular orbit, far enough out that the temperatures stayed near absolute zero. It did not change shape. It did not change color significantly. It did not break apart. It did not collide with anything bigger than a grain of dust. It simply orbited, in the dark, in the cold, for an interval of time so long that human language strains to hold it. When New Horizons photographed it in 2019, the spacecraft was looking at a piece of the universe preserved exactly as it had been when the planets were forming. Most of the surface of Arrokoth is dark red. The color comes from organic chemistry, from long carbon-rich molecules formed by the slow action of cosmic rays on simple ices over billions of years. The composition is mostly water ice, methane ice, and a few other frozen volatiles. There are faint craters, very few of them. There are smooth regions. The whole object looks calm, as if it has been resting. Arakoth is what the Kuiper belt mostly contains. Not dwarf planets. Not famous worlds with moons and atmospheres. Most of the belt is made of small objects like this, tens of thousands of them. Some larger, some smaller, almost all of them undisturbed, sitting in their long, slow orbits doing very little. The Kuiper belt is a fossil bed, and the spacecraft that visited the most studied fossil in it is still flying, looking for the next one. Before we go further out, we have to step inward to the planet that sits at the doorway of the belt. Neptune was discovered on the night of September 23, 1846, by a young astronomer at the Berlin Observatory named Johann Galle. He was acting on a prediction made by the French mathematician Urbain Le Verrier, who had calculated from the irregularities in the orbit of Uranus that another large planet must exist further out. Le Verrier sent his prediction in a letter. Galle pointed the telescope at the predicted spot. Within an hour, he found the new planet. Neptune turned out to be a pale blue world about 4 times wider than Earth. It orbits the Sun at an average distance of 30 astronomical units, completing one full circle every 165 years. That is a Neptune year. Since its discovery, the planet has completed only a single trip around the Sun, returning to roughly its discovery position in the year 2011. Neptune does something quiet but enormous. It runs the doorway of the Kuiper belt. Picture a child running fast around the edge of a wide, shallow pool of marbles. Every time the child passes near a marble, the marble gets kicked. Some get pushed inward, where other forces deal with them. Some get pushed outward, where they roll to a stable patch of floor. Some get pushed so hard they leave the pool entirely. Neptune does this with icy bodies, not by touching them, by the gravitational pull of its mass on anything that passes nearby. Any small object that drifts into Neptune's orbital zone eventually gets nudged. Over millions of years, those nudges sort the population of the outer solar system into stable groups. Some objects survive by locking themselves into stable orbital relationships with Neptune. They complete 3 orbits for every 2 that Neptune completes, or 4 for every 3. These relationships are called orbital resonances. Pluto is locked in a 3-to-2 resonance with Neptune. It crosses inside Neptune's orbit on every trip around the Sun, and yet it has never collided with Neptune, because the resonance ensures that the two are always on opposite sides of the Sun whenever Pluto reaches the crossing point. Other objects, the ones that did not find a stable resonance, got thrown. Some went inward, into the inner solar system, where they became short-period comets, swinging through every few years, brightening briefly, then fading back out. Others got thrown outward, into the wider regions of the belt and the scattered disk beyond. Almost everything in the outer solar system has Neptune's fingerprints on it. This is why the Kuiper belt begins where it does. The inner edge of the belt, at 30 astronomical units, is not a physical wall. It is a doorstep kept clear by a planet sweeping its threshold. Anything that drifts too close gets removed one way or another. Anything that stays settles into a stable pattern around the rhythm of Neptune's orbit. Neptune is also still pale and still blue. Its atmosphere is mostly hydrogen and helium, with a small amount of methane that absorbs red light and gives the planet its color. There are storms in its upper atmosphere, with winds among the fastest measured anywhere in our solar system, over 2,000 kilometers per hour. There are bands of cloud. There are dark patches that come and go over the course of years. There is a thin set of rings, barely visible. When Neptune was photographed up close by Voyager 2 in 1989, it became, for a brief season, the most beautiful object in the planetary photo album. The spacecraft had been launched 12 years earlier on a tour of the outer planets. It had passed Jupiter, then Saturn, then Uranus, and finally Neptune. The Voyager team gathered for the encounter and watched, in something close to silence, as the spacecraft sent back the first close-up images of a planet that had only ever been a faint blue point of light. What Voyager saw was a world with a great dark spot rotating in its upper atmosphere, with cirrus-like white clouds drifting above the spot's edges, and with the fastest measured winds in the solar system roaring around its equator. Voyager also visited Triton, Neptune's largest moon, and found a strange world covered in nitrogen ice with active geysers shooting dark plumes into a thin atmosphere. Triton orbits Neptune backward, against the direction of the planet's rotation. The most likely explanation is that Triton is not really a moon of Neptune. It is a captured Kuiper belt object, an icy world from the outer regions pulled into orbit around Neptune billions of years ago. Then, Voyager kept flying, and Neptune fell back into the long quiet. It is still there, slow and pale, sweeping the doorway. Beyond it, the belt begins. Now we go to the place the textbooks use to call the outer edge. Near the orbit of 48 astronomical units, the Kuiper belt does something strange. The count of icy worlds, which has been rising steadily as you look further out, suddenly falls, not gradually, not over a long stretch, sharply like a coastline. Astronomers call this drop the Kuiper Cliff. It is not a physical wall. There is nothing out there at 48 AU that you could collide with. The cliff is a feature of population. It marks the place where the icy worlds simply stop being there in the numbers you would expect. And this was a problem. The early models of how the outer solar system formed had predicted a slow, gradual thinning of objects with distance, not a sudden cliff. The expected curve was smooth. The observed curve was not. In 2003, an astronomer named Gary Bernstein, working with David Trilling and several colleagues, did the careful work. They used the Hubble Space Telescope to look at the outer Kuiper belt and applied statistical methods to ask whether the cliff was real or whether it was a trick of how the data was gathered. Faint objects far away are harder to see than bright objects nearby. Maybe the icy worlds past 50 AU were just below the detection threshold of the telescopes of the time. Bernstein and his team controlled for this. They calculated, for each distance, how bright an object would have to be for Hubble to detect it. They worked out what the expected count should be at each distance, assuming the population behaved the way the models predicted. Then they compared the prediction to what they had actually seen. The numbers did not match. Beyond 50 astronomical units, the population of large icy bodies fell well below what the models said should be there. It was not an instrument problem, it was a real feature of the solar system. The cliff was confirmed. For about 20 years after that paper, the cliff was the edge. The Kuiper belt ended at 50 AU. Beyond it, almost nothing. The sun's gravity still reached much further, all the way out to the distant Oort Cloud, but the dense belt itself stopped at the cliff. Nobody knew why. Several explanations were proposed. Maybe the early solar nebula had simply run out of raw material at that distance. Maybe an early massive object had wandered through the region and scattered everything out of it. Maybe the icy worlds further out were too small to detect, and a fainter population was sitting just beyond the threshold of our instruments. Each explanation had problems. The nebula explanation ran into trouble because most other planetary systems we observed, with their own dust belts and debris disks, looked much larger than the Kuiper belt. If our outer solar system was cut off at 50 AU, we were unusually small compared to our neighbors. The unseen object explanation ran into trouble because no such object had been found. The too small to see explanation was the most boring and also the hardest to test, because the only way to confirm it was to look harder, with deeper exposures, for longer. So for 2 decades, the cliff sat in the data, real and unexplained. Textbooks were rewritten around it. Diagrams of the solar system began to show a sharper outer edge to the Kuiper belt, ending neatly near 50 astronomical units. Lectures introduced the cliff as one of the unsolved problems of planetary science. New surveys, when they began, were designed around the cliff as a known feature. Anyone who searched past 50 AU expected to find very little. Often, that expectation was confirmed. The risk of an unsolved feature like this is that it shapes what people look for. If you believe the belt ends at 50 AU, you do not put your best telescopes on the volume past 50 AU. You put them on the bright, populated inner band where the discoveries are easier. The cliff, in this way, partly protected itself. It became the place we mostly stopped looking. It was not the end of the story. There was a region past the cliff that the old models could not reach, and there was a small number of objects out there, orbiting in ways that were strange enough to suggest something hidden. Sedna was one of them. Sedna is small, about 1,000 kilometers across, smaller than Pluto, made of ice, red in color, possibly the reddest large object in the solar system for reasons that are still being worked out. But Sedna's orbit is what makes it remarkable. At its closest approach to the Sun, Sedna is about 76 astronomical units away, past the Kuiper Cliff, beyond every classical Kuiper Belt object, already in a region the textbooks barely drew. At its farthest point, Sedna is nearly 1,000 astronomical units from the Sun. 1,000. Try to hold that distance. Pluto, at its average distance, is less than 40 astronomical units away. Voyager 1, the most distant human-made object, is currently around 160 AU after almost 5 decades of flight. Sedna goes out further than 5 times the distance Voyager has traveled, and then it comes back. One full orbit of Sedna around the Sun takes more than 10,000 years. When Sedna was last at its closest approach to the Sun, humans on Earth had not yet invented writing. The pyramids would not be built for thousands of years. By the time Sedna swings back to its perihelion in roughly 700 years from now, every present civilization will be in a future we cannot imagine. Sedna does not really live in the Kuiper Belt. It lives in a much larger structure called the scattered disk, a region of small icy bodies on highly tilted, highly elongated orbits, stretching from past the cliff out to roughly 1,000 AU. The scattered disk is where the Kuiper Belt fades into something else, where the orderly resonances of Neptune's influence weaken and the icy bodies begin to drift on stranger, lonelier paths. Sedna was discovered in November 2003 by a team led by the American astronomer Michael Brown at Caltech, working with Chad Trujillo and David Rabinowitz. They had been systematically searching the sky for distant, faint objects beyond Neptune. Sedna was one of the first true scattered disk objects ever found. It was named for an Inuit deity associated with the cold, dark sea. The name fit. Sedna spends almost its entire orbital lifetime in the deepest cold of the outer solar system. Its surface is too far from the Sun to warm meaningfully. Its atmosphere, if it has one at all, is frozen. Other scattered disk objects have been found since. There are now perhaps 100 of them with confirmed orbits, though the actual population is estimated at tens of thousands. Each one sits in a slightly different orbital geometry, with different inclinations, different elongations, different perihelia. Together, they sketch a region of the outer solar system that is much larger than the classical belt, much more diffuse, and much less understood. In 2014, 2 astronomers named Chad Trujillo and Scott Shepard announced the discovery of a second world that, like Sedna, never came close to the Sun. They had named it 2012 VP-113, with the more informal nickname Biden, after the United States Vice President of the time. Its closest approach to the Sun was about 80 astronomical units, even further out than Sedna's, and its full orbit took it out to thousands. The discovery of a second Sedna-like world made it possible to ask a harder question. Sedna alone could have been a freak object, scattered into its long orbit by some past gravitational accident. 2 such objects, with orbits that pointed in suspiciously similar directions, was a stronger signal. Trujillo and Shepard noted, in their announcement, that the orbits of the most distant known objects appeared to cluster. Their argument was cautious, the sample was small. But they suggested that an unseen, massive object might be responsible. The scattered disk is also where some of the strangest patterns in the outer solar system appear. If you look at the orbits of the most distant known scattered disk objects, the ones that reach hundreds of astronomical units, you see something subtle. Their orbits do not point in random directions, they seem to cluster. They lean, statistically, toward a similar orientation in space, as if something out there were nudging them into alignment. Most of the obvious nudges in the solar system are accounted for. The Sun. The 4 giant planets. Their combined gravity should produce a random scattering of orbits in the outer disk, not a clustered one. And yet, the cluster appears. When astronomers first noticed this pattern, sometime around 2014, the question that arose was natural and uncomfortable. Is there something out there we have not yet found? In 2016, 2 astronomers at Caltech published a paper that made the question harder to dismiss. Their names were Konstantin Batygin and Michael Brown. Brown was the same astronomer who had led the Sedna discovery a decade earlier, and who had played a central role in the reclassification of Pluto. He had a track record of finding distant worlds. Batygin was a younger theorist, an expert in orbital dynamics. Together, they looked at the cluster of orbital orientations in the outer scattered disk. They asked a careful question. Could the cluster have arisen by random chance? Their answer was that it could, but only barely. The probability that 6 of the most distant known objects would all line up the way they did, by coincidence, was estimated at about 1 in 15,000. That probability is small enough to suggest that something is forcing the alignment. Their proposed explanation was a planet. Not a small planet, not another Pluto. A large world, about 5 to 10 times the mass of Earth, orbiting the Sun at a distance somewhere between 400 and 800 astronomical units. They called it Planet 9. If it exists, it would be the 9th planet in our solar system. Larger than Earth, smaller than Neptune. Cold beyond imagining, far enough from the Sun that it would receive essentially no warming light. Its surface would be dark. Its orbital period would be somewhere between 10,000 and 20,000 years, and it would explain the clustering. The gravitational influence of a planet that big, at that distance, drifting through its slow orbit over billions of years, would gently herd the distant scattered disk objects into the lined-up pattern that astronomers had observed. It is important to say what the evidence is and what it is not. The evidence is a statistical anomaly in the orbits of a small number of distant icy bodies. It is real. It has been independently checked. Several research teams have confirmed that the clustering exists, that the probability of it arising by random chance is small, and that a massive distant object could plausibly explain it. What is not yet evidence is the planet itself. No one has seen Planet 9, not directly, not in any image, not in any survey. The hypothesis is, for now, an inference from the behavior of orbits, not a confirmation from a telescope. Other explanations have been proposed. Some astronomers argue that the apparent cluster is not real, that it is a feature of how the surveys have selected their objects rather than how the objects actually orbit. If you can only see distant icy bodies when their orbits bring them close enough to detect, you may end up sampling a biased population, and the cluster you observe may not reflect the underlying reality. Other researchers argue that even if the cluster is real, a planet may not be required. A massive ring of small bodies sitting beyond the cliff might provide enough gravitational influence to produce the same effect without any single large object. Each alternative has its problems. Each one has its proponents. The debate is, as of right now, open. In recent years, Brown and Batygin have continued to publish updates to the hypothesis. In one 2024 paper, they argued that the predicted Planet 9 would also subtly perturb the orbits of asteroids closer inside the orbit of Neptune, and that those effects, when searched for in the data, appeared to be present. Other teams have run independent simulations. Some have reinforced the original conclusions. Others have argued for lower probabilities of Planet 9's existence. A 2023 statistical study pegged the likelihood at around 40%, though even that figure remains contested. Mike Brown has said publicly that he is extraordinarily confident the planet exists. Other astronomers are skeptical. Some are agnostic and willing to wait for better data. What everyone agrees on is that better data is now possible. Telescopes have grown more capable. Computational searches have grown more efficient. New surveys, specifically designed to detect faint, slow-moving distant objects, are coming online. And one of them, the one most likely to settle the Planet 9 question, has only just begun watching. If this kind of slow walk through the cosmos is what you came for, leave a quiet like and tap subscribe. It is the simplest way to keep these long journeys reaching the people who like them. No pressure. One small tap. Then come back, because the next stop is the one that has changed the conversation. There is a telescope on the summit of Mauna Kea in Hawaii called Subaru. It has a single mirror 8.2 meters across, one of the largest in the world. It carries an instrument called the Hypersuprime Cam, often shortened to HSC, a wide-field camera that can photograph a patch of sky as large as 9 full moons in a single exposure. Since it began operations, Subaru has been one of the most productive survey instruments on Earth. Starting in 2020, a team of astronomers began using Subaru in coordination with the New Horizons spacecraft. The lead author of the resulting study was Wesley Fraser, an astronomer at the National Research Council of Canada. Fumi Yoshida, of the University of Occupational and Environmental Health Sciences and the Chiba Institute of Technology in Japan, led one of the deep image analyses. Alan Stern, the principal investigator of the New Horizons mission, coordinated the spacecraft side. Dozens of other scientists from observatories in the United States, Japan, Canada, and elsewhere joined the work. Their goal was simple to state and difficult to execute. They wanted to find faint Kuiper belt objects sitting along the future trajectory of New Horizons. The spacecraft had only a few kilograms of hydrazine fuel left. Any new flyby would require a target close to the existing path. The team needed to map the outer solar system in their flight corridor more deeply than anyone had ever mapped it before. Their method was patient. They picked 2 small patches of sky, each about 9 full moons across, lying along the spacecraft's path. Over 30 half-nights of telescope time, spread across multiple years, they took hundreds of exposures of those same patches. Then they used a technique called shift and stack. Shift and stack works like this. You take a stack of exposures and slide them sideways at the rate you expect a Kuiper belt object to move across the sky. Faint dots moving at that rate add up across the stack into a single brighter dot. Background stars which do not move smear out and average to nothing. The trick is that you do not know the rate in advance. Different distances produce different rates, so you have to try many shift rates, one for each possible distance an object might sit at. Each rate produces a different stacked image. Each image has to be searched. The whole process is computationally heavy. It takes weeks of computer time per patch of sky. By 2023, the team had used this method to identify around 240 new Kuiper belt objects in their 2 small fields. Most of them sat where the textbook said they would, between 30 and 55 astronomical units, inside the main belt. Then the team noticed that a small group of detections did not fit. 11 of the objects were sitting much further out, between 70 and 90 astronomical units, in a region that, according to every standard model of the outer solar system, should have been empty. These were not objects the team had been looking for. They had simply appeared in the data, almost as a side effect of the careful search. Each one was checked. The motions were cross-validated. The team had to be sure these were not noise, not poorly subtracted background stars, not optical glitches in the camera. Each check came back the same way. 11 faint worlds. Past the cliff. Drifting at distances no one had expected. When the team laid out the distribution of all their detections by distance, the shape was striking. A high count in the main belt, between 30 and 55 AU, then a sharp drop almost to 0, between 55 and 70 AU. Then a smaller cluster, the 11 new objects, appearing between 70 and 90 AU. 2 populations. Separated by a gap. The paper was published in the Planetary Science Journal, with Fraser as the lead author. The team was careful about how they framed the finding. The 11 objects were classified as candidates. Their orbits were estimated, but not yet fully confirmed. More observations would be needed to map the precise shape of each orbit, but the basic picture, even with the appropriate uncertainty, was clear. The Kuiper belt does not end at a cliff. The closer we look at the Kuiper belt's edge, the less of an edge it turns out to be. That is the sentence at the heart of this entire story. The wall, in other words, was not the wall. The cliff was not the cliff. The drop-off was a feature of where our instruments could see, and once the instruments improved, the line moved outward. How much further the belt actually extends is still being worked out. The 11 candidates may be the first sign of a second belt, sitting at 70 to 90 AU. They may be the inner edge of a much larger extended structure that continues to 100 AU or beyond. They may, in a smaller possibility that has to be considered, turn out on careful follow-up to be scattered disk objects rather than a distinct ring. What we know about the individual candidates themselves is limited. They are faint. Their sizes are roughly estimated from their brightness, and they appear to be somewhere between 100 and 200 kilometers across, similar in scale to the smaller objects in the main belt. They are too far away for any detailed imaging, They appear in the stacked data as small smudges of light moving slowly across the field at the rate expected for distant objects. The team has begun follow-up observations to refine the orbit of each candidate. This work will take years. The orbits of distant, slow-moving objects can only be pinned down by watching them across long stretches of time. Their estimated semi-major axes, their inclinations, their eccentricities will all gain precision as more observations come in. Whatever they are out there. And they are doing something the old textbook never accounted for. To understand why the 11 new objects matter so much, you have to step out of our solar system entirely and look at what surrounds other stars. Over the last 2 decades, astronomers have grown much better at imaging the dust and debris around nearby stars. Several telescopes have been central to this work. The Hubble Space Telescope, the Spitzer Space Telescope before it was retired, the Atacama Large Millimeter Array in Chile, known as ALMA, the James Webb Space Telescope more recently. Each one, in its own way, opens a window onto the kinds of structures that exist around other planetary systems. What these telescopes have shown is that almost every nearby star with planets also has a disk of leftover material around it, a debris disk. Dust and small bodies, the remains of whatever did not get bound up into planets when the system formed. These debris disks are the closest thing other stars have to a Kuiper belt, and on average, they are larger than ours. A typical debris disk around a star roughly the size and age of the Sun extends to about 100 astronomical units from its central star. Some extend further. The disk around the star Fomalhaut, for example, sits at about 140 AU and has been imaged in beautiful detail by Hubble and Webb. The disk around Vega, the bright star in the constellation Lyra, is broader still. Even the more compact systems usually reach out to 70 or 80 AU. Compared to those numbers, our Kuiper belt, ending near 50, looks small. ALMA, in particular, has done something the older telescopes could not. It has imaged the outer disks of much younger planetary systems with enough detail to show their internal structure. Around the young star HL Tauri, ALMA revealed a series of concentric bright rings and dark gaps in the surrounding disk, looking almost like a tree's growth rings seen from above. Around PDS 70, ALMA traced another pattern of rings, with newborn planets sitting in some of the gaps, slowly clearing their orbital lanes. These images mattered for the Kuiper belt because they showed that ring and gap structures are not unusual. They are a common feature of how planet-forming disks evolve. If our outer solar system has its own ring and gap pattern hidden beyond the cliff, it would simply be following a template that other planetary systems are known to share. This is the comparison that began to make some astronomers uncomfortable in the 2010s. If our solar system is, in most other respects, ordinary, then why should its debris disk be unusually short? Why should our belt stop near 50 AU when the belts of our cosmic neighbors stretch to twice that distance and more? 2 answers were possible. The first answer was that we really were unusually small. Maybe the early nebula around our Sun had truncated for some reason. Maybe a passing star had stripped off the outer layer billions of years ago. Maybe an early massive object had cleared the region. In any of these cases, our Kuiper belt was simply shorter than its cousins around other stars. The second answer was that the cliff was an illusion of our instruments. Maybe our belt did extend to 100 AU, like the others, but the population past 50 AU was too faint or too few to detect with the surveys we had run. In that case, we were not unusual. We were simply under-equipped. Wesley Fraser, the lead author of the new survey paper, has put the question this way. The Kuiper belt has always looked unusually small in comparison with many other planetary systems. That idea, he has said, might have arisen purely from an observational bias. We could not see the outer parts, so we concluded they were not there. The discovery of the 11 candidate objects past the cliff suggests Fraser was right. The Subaru survey was sensitive enough to detect faint objects out to roughly 90 AU. When it looked, it found them. The cliff held for the population of large objects, which had been the original Bernstein finding. But a fainter population sat further out, and once the instruments could reach it, the population started to appear. If this is correct, then our solar system is not the anomaly the old maps suggested. Our outer disk may stretch much further than the textbooks have drawn. Possibly to 100 AU. Possibly further. The 11 candidates may be the first detections in a much larger population that we have, for 30 years, simply been unable to see. The other planetary systems in this view were always telling us what to expect. We were not unusual. We were undercounting. On a mountain in northern Chile called Cerro Patron, an 8.4-meter telescope has just begun the largest sky survey in history. It is called the Vera C. Rubin Observatory, named for the American astronomer who provided the first convincing evidence for the existence of dark matter. Vera Rubin spent her career, much of it in the 1970s and 1980s, measuring the speeds at which stars orbited the centers of distant galaxies. What she found was that the stars at the outer edges of those galaxies moved too fast to be held in place by the visible matter alone. Something invisible, much heavier than everything we could see, had to be holding the galaxies together. That something is what physicists now call dark matter. The observatory carries her name because its survey will, among many other things, map dark matter more precisely than any survey before it. The telescope sits inside a white dome at the summit, and it carries the largest digital camera ever built, weighing nearly 3,000 kilograms with 3,200 megapixels. First light was achieved in June of 2025. The observatory officially handed over from its construction team to its operations team in October of the same year. The full 10-year survey, called the Legacy Survey of Space and Time, has begun operations in early 2026. What Vera Rubin will do for the next decade is photograph the entire visible southern sky every few nights. Each individual image covers an area about as large as 45 full moons. The telescope can move quickly between targets, taking new exposures every 30 seconds. Over the course of 10 years, it will return to every patch of the southern sky roughly 800 times, building up a time-lapse record of everything that changes. Asteroids, comets, variable stars, supernovae in distant galaxies. Whole populations of objects that are too faint to be caught by any single survey will emerge from the cumulative depth of Rubin's repeated visits. For the Kuiper Belt, this is the survey everyone has been waiting for. The 11 candidate objects discovered by the Subaru team will be observed again and again by Rubin, often enough that their orbits can be pinned down with much greater precision. If they really do form a second belt at 70 to 90 AU, the structure will become clearer. If they belong to the scattered disk, after all, the data will say so. Other unknown populations may also emerge. The kind of fainter, more distant objects that current surveys have missed will start to appear in Rubin's deep stacked images. If there is a second ring beyond the cliff, Rubin will probably find more of its members. If there is a continuous, extended population reaching out to 100 AU, Rubin will probably map it. And Planet 9, if it exists, may finally be detected. Rubin's wide field, long exposures, and repeated scans give it roughly a 70 to 80% chance of detecting Planet 9 if Planet 9 is real and sitting somewhere within the predicted distance range. That is, according to Scott Shepard, an astronomer who has spent years searching for distant trans-Neptunian objects. If Rubin finds it, the cluster of distant scattered disk orbits gets its planetary explanation. If Rubin does not find it after 10 years of searching, the hypothesis becomes much harder to sustain and the alternative explanations gain ground. Either way, the answer is now within reach. Over the next few years, the data releases from Rubin will reshape what we know about the outer solar system. The 11 candidates will be confirmed or refined. The cliff will become clearer. The second belt, if it exists, will be mapped. The shape of the outer Kuiper belt will be pinned down with a precision that has been impossible until now. By the end of the survey, the diagram of the solar system in every textbook will probably need to be redrawn. The scale of the project is hard to picture. Each night, Rubin operates. The telescope generates about 20 terabytes of data, more than most major observatories produce in months. The processing system attached to it pushes alerts out within 60 seconds of each observation, anywhere from a few 100,000 to 10 million alerts per night, telling astronomers around the world that something has just changed in the sky. Each alert includes the object's brightness, position, and the cut-out image of the field where the change was detected. The first such alerts began going out in February of 2026. Out of all those alerts, only a small fraction will be objects in the outer solar system. But that fraction, over 10 years, will be larger than every previous outer solar system survey combined. The smudge past Neptune will not be a smudge anymore. It will be a structure, probably a larger one than the one we have been used to drawing, possibly with rings and gaps and an extended outer population that we have only just begun to see. And then, past all of that, sits the largest and least visible structure of all. The Kuiper belt, even with its second belt and its faint extended population and its 11 candidate objects, is not the end of the solar system. Past the belt, past the scattered disk, past Sedna on its long arc, there is one more region. We have never directly imaged it. We have inferred it almost entirely from the behavior of long-period comets, the ones that swing through the inner solar system every few thousand or 100,000 years, falling in from impossibly distant orbits. It is called the Oort Cloud. It is a vast spherical shell of icy bodies surrounding the entire solar system. Not a flat ring like the Kuiper belt. A sphere. The Sun and all its planets and all of the Kuiper belt sit inside it like a marble inside a glass ornament. The Oort Cloud is thought to begin around 2,000 astronomical units from the Sun, 20 times further out than the 11 candidate objects, and to extend outward to perhaps 100,000 AU. That outermost distance is about a quarter of the way to the nearest neighboring star. There may be trillions of icy bodies in the Oort Cloud, maybe more. The total population is one of the least constrained numbers in astronomy. Almost all of them have never been seen, and probably never will be, individually. They are too faint, too distant, too small. What we know about them comes almost entirely from the few that occasionally fall inward, becoming long-period comets, briefly visiting the inner solar system before vanishing back into the dark. The idea of the Oort Cloud was first laid out in 1950 by a Dutch astronomer named Jan Oort. He had been thinking about the orbits of the long-period comets that occasionally appeared in the inner solar system. Each one came in from a direction in the sky that seemed essentially random. Each one swung past the Sun on a long, elongated orbit that stretched out for tens of thousands of years. Oort noticed that the orbits, when traced backward, did not point to any single source in the plane of the planets. They pointed in every direction at once. That was a clue. It meant the source of the comets was not a flat disk, like the Kuiper belt. It was a sphere, a shell surrounding the entire solar system on all sides. Oort calculated where such a shell would have to be, given the comet orbits he could observe, and he placed it at thousands to tens of thousands of astronomical units from the Sun. His reasoning has held up. Every long-period comet observed since 1950 has been consistent with an origin in roughly the region Oort described. The cloud has never been directly photographed. We have no individual image of any single Oort cloud body in place. We know it is there because every few years, one of its members falls inward, and we see the small bright trail of its passage through the inner solar system. The Oort cloud is the real outer edge of the Sun's gravitational reach. Past it, the Sun's gravity weakens enough that other forces, the gravity of nearby stars, the tidal pull of the galaxy itself, begin to matter more. And once you can hold this whole picture in your mind, something interesting happens. The idea of an edge of the solar system starts to feel uncertain. The first edge was Pluto's orbit, when Pluto was a planet. Then it was the Kuiper Cliff at 50 AU. Then it was the gap at 55 to 70 AU. Now the new candidates have pushed the boundary out to 90 AU, possibly 100. The scattered disk extends past 1,000 AU. The Oort cloud reaches 100,000. Each time we have been certain about where the solar system ends, the next round of observations has moved the line. The closer we look at the edge, the less of an edge it turns out to be. That sentence has returned now for the third time. In the hook, it was a suggestion. In the survey results, it was a confirmation. Here, at the end, it is something simpler. A way of seeing. The universe out there is continuous. It thins. It gets darker. It gets stranger. But it does not actually end at any of the lines we have drawn. The Kuiper belt we have on every textbook poster is the Kuiper belt of 1992 and 2003, drawn with the tools of those decades. The Kuiper belt of the next decade will look different. By the time the Rubin survey is finished, the shape of the outer solar system will be one of the clearer features in modern astronomy. The new shape will probably extend further than the old one. It will probably include the 11 candidates and many more like them. It will, in some way, surprise us. What it will not change is the way it feels to think about this from inside a quiet room. Right now, where you are, the Earth is moving along its small orbit around the Sun. The Sun is moving along its much slower orbit around the center of the galaxy. The galaxy is moving toward the constellation Hydra at a speed nobody on Earth can feel. All of these motions are happening continuously without your participation, in scales you do not need to track to live your life. And out there, in the same volume of space, the Kuiper belt is also drifting, slowly, quietly. Billions of kilometers away, the 11 candidate objects are completing their long, cold orbits. The scattered disk is doing the same. Sedna is making its way back from 1000 AU toward its closest approach, which will not happen for centuries. The Oort Cloud is doing whatever the Oort Cloud does, in the dark, where no telescope has ever directly seen it. All of this is happening right now, as you breathe, as you settle into the bed, or the chair, or the place where you are listening from. The room you are sitting in is small. The window above you, if there is one, opens onto a thin slice of sky. But the same sky, followed outward, leads to a region we have only just begun to map. The Kuiper belt does not need us to look at it. It does not need us to draw it correctly. It will keep being the size it is, regardless of what we put on the textbook page. We are, for now, learning to see it again, and tonight, that is enough. Good night. If you stayed with me this far, thank you. If these long walks help you sleep or help you wonder, leave a quiet like before you drift off. It is a small thing, and it helps the channel more than you might think. Sleep well,